Let's have a leisurely start to the day. I can see you're enraptured by this. That better? Probably is, but I can't actually see what you're doing. Maybe that's the way to do it. Interesting stuff. Yeah, pretty cool. So, all by way of saying that today, I guess the real point was going to be maybe this. And that is, we'll talk about properties of fluids starting today. And of course, fluids can exist, materials can exist as a solid, and fluids can exist either as liquid or a gas, as you see both of them here. And they have certain properties that define their behavior. So that's the first material that we'll talk about today. So that's our plan for today. Usually there's something interesting in the news that might relate to fluids. I don't know that necessarily there is today. The news seems to be taken over with other stuff. That's interesting enough. But there certainly is a hurricane or a cyclone that's offshore Hawaii, which is a fluid mechanics issue. Issues of storm surge and the battering winds, both the atmospheric part and also the oceanic part in terms of the high tides are part of it. Now, recently gone off the front page was this bridge collapse in Genoa, Italy, maybe 5 days ago, certainly last week. And obviously that's not fluid mechanics, but certainly since many of you are aspiring to be and will be engineers, will have a seal which you will stamp drawings with. There's a certain level of trust that goes with that as a member of that profession. That's why you have to take an EIT exam and then the PE exam after 5 years or so. The expectation is that you ensure public safety. And so one of the reasons why this class isn't really on a curve is because there's a minimum standard that you have to reach so that you're not dangerous to people. And so that's part of the rationale maybe of why we grade this class in the particular way that we do. I don't think it's disadvantageous to you the way it is, because it turns out I think that there are more A's in this class than there would be otherwise, just based on the way that we do it. But that's the rationale for that. So what we'll do today is, like any day, we'll go through a sequence of material. If you downloaded the notes and looked at them, you'll see that they conform to this. So we'll go through this and probably get down to talking about compressibility, about this far. And we'll go through it incrementally. Just as an offside here, one of the things that I saw that was still on my desktop are the review materials that are used in the video for midterm number 3. And so typically you can get some feel for what these exams will contain, certainly based on the material that's covered, identified here. 3 questions, identifying what parts of the material in that 4-week session of class. The questions will be drawn from, and then some discussion of the principles that you need to be able to do that. Stuff that you perhaps don't know yet because we haven't got to weeks 11, 12, and 13, which is what this is taken from, to be able to deal with this. So I don't need to keep that there. I'm going to get rid of it just because I don't need it. But anyway. In terms of the syllabus, you'll see that when we look at this, maybe I'll look at this in full screen view. The first part of the syllabus deals with fluid statics. So the first 2 weeks we'll talk about fluid statics. The third week we'll look at how fluid pressures change in accelerating fluids. And then after that we'll look at fluid dynamics, if you like, starting at week 4 and 5 for Bernoulli. Different ways of looking at it. The one thing that you need from physics 2:12 is you need to know Newton's second law, F equals ma. That's the one piece of information that you need for this class. And we'll talk about conservation laws in weeks 7, 8, and 9 for momentum, for energy, and I guess for mass in 6, 7, and 8 is mass, momentum, and energy. We'll talk about using non-dimensional numbers in similitude in week 9. Then we'll talk about the applications of this. I said at the end of the class it gets more recipe-like. And so how do you calculate how much flow will go down this pipe? And so the questions become much more predictable. And so in weeks 10 and 11 we'll talk about internal flows, flows in pipes. In week 12 we'll talk about external flows, flows around aerofoils, for example. And in week 13 and 14 we'll talk about open channel flows. And so that's kind of a potted discussion of exactly where we will go. So we'll start off that by talking today about fluid properties. It's always good maybe to have a motivation of why we might be doing things. So maybe we'll spend the first little while talking about fluid mechanics in some different systems. Certainly we know that if you look at the March 11th, 2011 East Japan earthquake, or the Boxing Day earthquake from much earlier in your lifetimes of the 26th of December 2004 in Indonesia that killed 200,000 people with the tsunami that came from it. Then certainly the Earth's mantle is a fluid system with molten magma in the mantle that convects by radioactive decay from elements within the core, and these cause the plates on the plate boundary to move and to subduct, and to volcanoes to develop where they melt, and also for earthquakes to occur close to these subduction zones. These earthquakes, when they let go, can result in differential displacement on the seabed. And if you imagine this differential displacement is enough to basically make an initial wave, and that is the origin of tsunamis. And of course, these are some pictures from the Boxing Day 2004 event in offshore Indonesia, which had a terrible death toll and kind of re-energized the world to the fact that, or reminded the world, because there certainly had been historic tsunami that might be 10 meters in height before, but not in historic times. And so it aligned the world to the fact that these things could occur and that you needed to provide some kind of warning from them. Weather systems and circulating in the atmosphere and the tidal effects, as we just mentioned, are also fluid mechanics systems. Ice sheets creeping on Greenland move very, very slowly, but they're basically fluids, but very viscous fluids that move very slowly. The Deepwater Horizon disaster of 2010, was it? With the BP oil well that went off in the Gulf of Mexico, clearly is a natural phenomenon, man-made, human-made phenomenon, but one which affects us through the circulation of the currents within the Gulf of Mexico. And yes, definitely before your lifetime, right? 38 years ago, May the 18th, 1980, was when Mount St. Helens, sitting very nicely in eastern Washington, decided that it wanted to blow. A huge lateral blast killed 60 people because everyone had been evacuated. It's not a very big death toll, but cast ash over the whole of the country, mostly in the northwest, but also in the rest of the country. In terms of engineered systems, fluid mechanics is all around us. Every time you take a flight, obviously, the principle of an airfoil is one that relies on fluid mechanics. The Deepwater Horizon is one that we just talked about. Every time you make a flight, if you get on one of the small planes in State College and you walk up the step path into the cabin, you'll see sitting on the side of the fuselage just below the cockpit, typically a pitot tube, still used to be able to measure wind speeds, to be able to know exactly where you're going to complement GPS. For those of you who are fuel scientists, internal combustion engine, obviously, getting a fuel mixture into the top of a cylinder, having it combust and expand and drive chemical energy into mechanical energy of the system is a fluids problem. If you live in New York City, or I guess if you live in State College as well, the whole issue of getting natural gas circulated around the country is done by a series of pipes. In addition, you may or may not know that in northwestern Pennsylvania, there's a whole bunch of salt domes in which gas is stored in big long cylinders, holes drilled down into the subsurface, then the casing slowly withdrawn, and fluid circulated at the bottom to dissolve these long cigar-shaped features, which might be 1,000 feet tall, but which can be used to store natural gas underground so that when everyone turns their ovens on in New York City at 7 o'clock in the morning, it's close to market. Vertical axis wind turbines, wave machines, articulating with the waves so you can get work out of that joint if you do it appropriately to be able to recover mechanical energy and turn it into electrical energy typically. You've probably seen the Tacoma Narrows Bridge, which were designed, bridges before the 1950s were designed without much thought of wind loads on them. And in this particular case, the issue was one of resonance. The frequency, the characteristic vibrational frequency, you take a ruler over the bench and you flick it, that's the characteristic frequency of that particular structure. If the wind excites it at that particular frequency because of the eddies that get shed off from the top of the bridge and then the bottom of the bridge in sequence that excite it, then all of a sudden if that characteristic frequency from the wind matches with the characteristic frequency of the bridge, you have problems. And in other areas, contaminated groundwater, recovering geothermal energy from the deep subsurface by circulating cold water down, picking up heat and bringing up hot water, and also in hydraulically fracturing gas shales, which has been a big boon to the economy of Pennsylvania in the recent past, are all fluids in porous media. Not open fluids in a room like this, but fluids that are constrained within the pore space of porous media. And in recreation, of course, the way that sails work is akin to how an airfoil works, very, very similar. And we'll talk about airfoils. The innovation, I guess, for the New Zealand team, well, it must be 15 years ago or more, when they stole the America's Cup, or was it the Australians, by having this secret fin on the bottom of their keel that allowed them to reduce drag and retain control of their boat better than the ones which didn't have that at the time. Every time they put it in the water, it would have a shroud on it because at that time it was secret. Maybe the Sydney Olympics. I'm trying to think when that was. It might have been at the limits of your life. Maybe in 2000 were the Olympics in Sydney, when the swimmers would wear bodysuits to be able to reduce drag. Since banned, I guess, just as a convenience. But there was at least one Olympics where suits were allowed. And in playing golf, why are golf balls dimpled? Surprisingly, it turns out that if you have rough air, turbulent air close to the golf ball, it actually has less drag than if it's a nice smooth surface. And so it will actually fly faster if it breaks into turbulent flow immediately around us. You can spin baseballs. Why do they curve in the way they do? Again, a fluid mechanics problem. Same for footballs. No doubt when you choose your projects for this class, many will choose rifling on a bullet, spinning a football, and we'll try and get it down to only one team. So if you want to get that in when it opens up, get that information in. And also snowboarding, well, gravity drags you down, friction on the base, you have wind against you as a wind resistance, so partly a fluid mechanics problem. Whitewater boating much more so, surfing on a wave, static within a river in a wave, the water going past you provides drag on the boat, you're facing down the wave and you have gravity going with you, so you have something pulling you back and gravity pushing you forward, and if you balance those exactly, you can sit on a wave and surf it. Surfing West Virginia, as the bumper stickers say. So that's kind of the motivation, hopefully, in terms of some of the things that we might want to try and do. So what we might do is we'll try and talk a little bit about introducing what we'll talk about today is what fluids are. We'll talk about dimensional homogeneity of equations and what the important properties are of fluids that we might want to worry about. I like to, it's kind of interesting that with all the evolution of education and PowerPoint for this, I think there's nothing worse than being stuck with a PowerPoint slide. So I tend to write on the board. My version of writing on the board, though, is actually writing on these spare pages that we have here. So I can either write on here, or I guess I can write on here. Why don't we do that for a change? So, where are we? 10 sparks, you'd say. I wish they had a chair for me sitting here. I'm going to become a hunchback by the end of the session. So let's talk about fluid properties. You've seen, of course, that I've started recording this, so you'll be able to see this. I saw that one person had noted that he or she was the first person to see the video from Monday, so that is already posted. So maybe look at the properties that are important for our consideration of fluids. And so we can look at solids. And gas. And so they come in a variety of different forms. You certainly know what these differences are. And so you kind of know what a solid is. The solid is my head. Liquid flows with a free surface. If you're here early, you saw the ice cube on the hot pan. If you melt the solid, it becomes a liquid, and if you keep on applying the heat to it, then it evaporates and it fills the space that's available to it. So a liquid has a free surface. If we look at the properties that these entail, then density is one of them. It is equal to the mass divided by its volume, and in our parlance, we'll call it rho. And so typically solids have a high density. For better argument, liquids have a medium density and gas a low density. Of course, that's not quite true for water, because an ice cube floats on water, and so it must be less dense than, the solid must be less dense than the liquid for it to float. But this is in general for materials. And so in terms of, we will use in this class only SI units. And so the units of density are kilograms per meter cubed. Viscosity. Well, you don't need to worry about this right now. We will define this. The term we will use for viscosity is mu. And not surprisingly, solids are very viscous. Gases have low viscosity, and liquids again are medium viscosity. The units of viscosity are newtons per meter squared times seconds, which are also the same as Pascal seconds. This is a Pascal. And so things like, well, you can think of things as glass as a solid, but it flows at very slow rates. Ice, you think of as a solid, but it also flows in glaciers. And so they're highly viscous, and so viscosity is some measure of the resistance to flow, I guess, in some respects. And a final property that we'll use is elastic modulus. And we'll define that later on today as applying a pressure and how density changes with that pressure. This is density, rho. This is P for pressure. This is elastic modulus. And again, solids have a high modulus, liquids medium modulus, and actually gases a low modulus. The other term that we'll use is the inverse of elastic modulus, and that is compressibility. And that is just, I'm not sure what we call it here, but we'll call it 1 over the bulk modulus EV. And so obviously these are the opposite of these because it's just the reciprocal. The units of elastic modulus are pascals, which we said are newtons per meter squared. And so the units of compressibility just have to be pascals to the minus 1 over pascals. And so those are the fundamental fluid behaviors that we will use in this class. So density is defined by rho. Viscosity is by mu. We won't use elastic modulus so much, but it's defined by bulk modulus E sub V. And these are the SI units that define them. So we'll work only in SI units in this class. So we'll develop a variety of expressions to define behavior. And although you can't necessarily tell whether an equation is correct by looking at it, what we can do, actually, why don't I talk about this figure first? Let me make this figure big. So I don't know why particularly I've chosen CO2 as the phase diagram that we use here. But if you look at where we are here, just to explain what you probably already know, is that we, at our current pressure and temperature, are what? In terms of absolute pressure, we are at 101 kilopascals, which is about 0.1 MPa, megapascals. And in terms of temperature, we are about 20 degrees C, which is about 273 plus 20 degrees Kelvin, right? And so this is in units of Kelvin. So if you look at where we are now, in terms of temperature, we are basically 293, so we are somewhere like here. In terms of pressures in bars, 1 bar is 1 atmosphere. So at the present, we are sitting here. So this is our current location. So I guess this is 1 bar. I thought it was MPa, but it's actually in bars. So that's where we are. And so at room temperature and pressure, then not surprisingly, CO2 is a gas. If we cool it and go from this point to this point, ultimately we'll cross here and it will be frozen as a solid. We'll go directly from a solid gas to a solid. Likewise, when we come back, if we heat it up from this at room temperature, it will sublimate. It'll go directly from a solid to a gas without crossing through a liquid. If we were at a higher pressure, so in other words, if our pressure was actually 10 times atmospheric pressure up here, then when we did the same as we went from this, we'd freeze it, we'd go first to a liquid CO2 and then to a solid. And so those are the phase behaviors that we expect to do if we're changing temperature. If we're changing pressure and keeping it at the same behavior, and we go up in this direction, then again, as we increase the pressure, it'll go from a gas to a liquid to a solid, but it will always be subcritical because it won't be in this region. If we were, instead of at 20 degrees centigrade, if we were at 35 degrees centigrade above, so in other words, we'd be 278, 88, 98, 308, then we would go from here into this region here. And so I'm not sure really why I use CO2 instead of water. We could use anything. CO2 is an interesting fluid these days because it's a greenhouse gas and there's plans to maybe sequester it by pumping it into the ground. And if you pump it into the ground as a supercritical fluid, certainly the temperature in the ground is 30 degrees centigrade plus. Once you get down 1,000 feet or a couple of thousand feet, then a supercritical fluid has two very important properties, has a number of properties, but it basically has the density of a liquid, but the viscosity of a gas. And so it means that you have a large mass of CO2 per unit volume that you can pump, but it has a very low viscosity, so it's not very difficult to pump it down a pipe and into the much more resistive formation that has to go in once you're in there. So the desire is to, if you are to dispose of supercritical fluids or CO2 in the subsurface, then you'd like to do it as a supercritical fluid, and you almost have to do it as a supercritical fluid because the geothermal gradient is about 20 degrees centigrade per kilometer. We start off here at 20 degrees centigrade, down 1 kilometer you're at 40, 80, etc. So you're already in this region of high temperature, and certainly once you get down in the subsurface, you are progressively higher and higher pressures. So it just is fortuitous that it ends up being a supercritical fluid. Okay. So phase behavior. So as you see, I won't go through everything in here. I started making the point that when we deal with fluids, you'll have lots of expressions to deal with. And all the expressions we'll deal with in this class, maybe with the exception of one or two, are all dimensionally consistent. If you're a petroleum engineer, almost all the expressions you'll use in your profession are material property dependent. They have to be in inches or PSI, and the units can't be in KSI, they have to be in PSI to get the right results. But all the ones we'll use have to be in specific units. And all the ones we use will not have to be in specific units. They have to be appropriately consistent. And so the point is that you can always check, you can check whether your equation is wrong, I suppose, is the point I would make. So for instance, if we talk about dimensionality. Then, so for example, if you look at the behavior calculating the area of something. So if you want to calculate the area of this between x0, x1, y0, y1, then certainly you know that the area is just equal to an integral dx dy, and this is between x0, x1 and y0, y1. Right? You know this because one of these little differential cubes here is going to be dx on edge and dy on edge. Hopefully you can see that. And so when you look at this, you know by definition that the units of this have to be in length squared. And in our terminology, that's in meters squared. If you make that integral, then you'll end up calculating that it's equal to this evaluated between these limits, which is the same as x1 minus x0 multiplied by y1 minus y0. And so the units of this have also to be, this is exactly what you'd know from this expression here, the units of this also have to be in terms of meters squared or length squared. And so the point I'm trying to make is that you can forget these operators, the differentials in this, and you can always check whether the left side of the equation and the right side of the equation make sense in terms of dimensional homogeneity. If they don't, then it means the equation can't be right. It doesn't mean the equation is right, but it means that the equation cannot be right if that requirement isn't met. And so in this class, we will only really use one equation from Physics 2012, and that is the one that will get used in Bernoulli. And so Bernoulli's equation basically takes a system which is x and z. We have a flow tube that converges in some way, and at a point we have fluid with some velocity attached to it, and that fluid is at some height z. What else do we need to define? And it also has some fluid pressure attached to it. And so we can write Bernoulli's equation in terms of something we'll derive in due course, but in terms of terms that you will already have met this morning. And so Bernoulli's equation is a term that represents the potential, the pressure, and, if you like, inertia or momentum, whichever you prefer. And so if you write that in a slightly different way, you can write that as F minus ma equals 0, just because of this. And so these terms on the left are the forces that are applied by the potential of a piece of water that exists at some height, or by the fluid pressures that are acting on the surface, and its motion, trying to accelerate it by moving it along a streamline, is counteracted by this. And so because these are all added together, by definition, they have to be the same units. Right? And so we can check that that's the case. Well, what the units are. This is elevation, so they have to, this equation has to be homogeneously written in terms of units of length. And so we could check whether that's the case just by taking one of these terms out. V squared over 2g. Is that going to be the case? So v squared over 2g. So what's that? That is written in terms of velocity squared is meters per second. It's squared. We don't care about the 2 because we're just looking at the units and equating those. And g is an acceleration. And acceleration is in terms of meters per second squared. Which indeed is in terms of meters. And so we can use that to be able to make sure that that equation makes sense. And so it must make sense, right? Just because we've done that. The other things that we can do with that is we could manipulate it in a variety of ways. I'm not sure whether we necessarily need to do that. I'm trying to think whether in terms of these different terms. The other things that we can do, of course, if I try and keep this on the same location, is we could divide term by term. And so, for instance, what we could do is we could divide a pressure term divided by the inertial term. So if you look at pressure divided by inertia, then what do we get? Pressure is pressure over rho g divided by v squared over 2g. Get rid of the g's, we don't care about the 2, and we end up with something which is pressure divided by rho. Don't mix up rho's and p's, they look the same, over v squared. And this is called the Euler number, which we'll use in pipe flow and in forces of wind on structures, for example. Or we could divide through the potential energy. Which one do I want to do? We could divide inertia by potential, which would be equal to, if I do this here, these two numbers. So this and this. I need to move this up a bit. And if we do that, inertia is v squared over 2g, and potential is 1 over z, which if we ignore the 2, we end up with v squared over gz, which is the same as v over, if we take the square root, gz, which is the same as what we'll call the Froude number. And so it's just a matter of manipulating these expressions to be able to define what's behavior. And the Froude number says something about when you drive a ship through an ocean, the size of the wave that you get. It looks at free surface effects in those. And so we'll deal with that when we deal with that in due course. If we look at, we said before, and this is perhaps a useful item to deal with, and that is that we can define a variety of these terms, and you can use one of two systems. We'll tend to use mass, length, and time, which would be kilograms, meters, and seconds. But you could also use force, length, and time, which would be in terms of newtons, meters, and seconds. So we'll tend to use this. So all of the expressions that we'll use, and we've already done it, we already looked at what the units of acceleration are. Length, meters per second squared, as this. And most of them are straightforward, but of course some of them perhaps aren't as obvious as others. So the easiest way to get some of them are to use quantities that make sense to you, that you can convert into the ones that don't make sense to you. And so force perhaps isn't an obvious one, but we know from Newton's second law that force equals mass times acceleration. And we know that mass is m, and we know that acceleration is meters per second squared. And so you can get it directly from looking at what those individual components would be, right? You can assemble them. So you just have to go back to something that you know that you can put together in some way. And so dimensional homogeneity is an incredibly important feature of what we do. You can check whether, as I say, whether equations are potentially correct, not whether they're absolutely correct. You'll see that in here, not only do we have mass, length, and time, but we also have something that has to represent temperature. T in temperature, in this particular case, temperature is given by this in the book. We will use temperature very seldom in this class. You use it a lot in thermo, but not in this class. Okay? So dimensional homogeneity is important. Okay? Reference systems. So let me see where this is. If we look at pressures, reference pressures and temperatures. I'm guessing you also know this, and that is that if you look at pressures, then you can look at scales that represent behavior both in terms of absolute and gauge. Or is that the right spelling or not? So in terms of absolute pressures, this is atmospheric pressure. So in terms of absolute pressure, then zero pressure absolute is this. Atmospheric pressure is 101 and change kilopascals. If you define it in terms of gauge pressure, then we take the pressure that you feel here at sea level today as 0, and therefore absolute zero pressure is negative 101. So if you're using gauge pressure, then this is 0, kPa, and this is minus 101 kPa. So this is important because when we look at pressures, whoops, this has gone crazy. Okay. Oh, I didn't mean to do that, did I? Okay. So when we look at this, this is absolute pressure, and this is gauge pressure. Likewise, when we look at temperatures, the same applies. And it's important to make this distinction. And this is absolute. And so this would be 0. This would be 0 degrees C, which is plus 273 Kelvin. And absolute 0 would be minus 273 degrees C. So this is absolute, and I guess this is Celsius, right? Or centigrade. And so this is important because when you look at using these, we look at the behavior of fluids, we'll often use the ideal gas law. Pressure is equal to density, gas coefficient for that particular material, and temperature. These are always absolute. Always. They have to be. Otherwise, that expression doesn't work. And so be careful when you do that, that you're using the right units. We can also write this as pressure is related to a mass divided by a volume, because that's exactly what density is. Again, times a gas constant for that particular material. So this is constant for gas I, whatever that gas is. If you want to couch it in terms of the universal gas constant, then you can also write this expression just as equal to, just going back to this first one because it's most convenient, the universal gas constant, which is a single number for all gases, absolute temperature, and the molar weight of the gas. And this is the universal gas constant. So, yeah, okay. So we've still got 5 minutes. Right. So it's important for us to be able to understand behaviors of gases. We made the case also that we can say something about, if we zip through this, we've gone through this, it's all in what we've talked about. If we talk about ideal gases, this is exactly that. We can think of expanding gases in a couple of different ways. We can compress them at constant temperature. And so, in other words, if you compress the gas in a bicycle pump, but you keep the outside temperature the same all the time, then the values of the terms on this left-hand side will be the same. And so you can just, since the temperature isn't changing and it's still the same gas, you can write the pressure of that gas divided by its density is going to be a constant as you squeeze it. So if you increase the pressure, the density will increase in exactly the same proportion as suggested just by writing, for instance, you could just write pressure 1 divided by density 1 is equal to RT, which is equal to pressure 2 over density 2, which is really what this is just saying, right? It's equal to single gravity. And so as the pressure increases, so will the density, so this doesn't change. If you compress it isentropically, so in other words, you take the pump and you put it in styrofoam, so none of the energy escapes, so the temperature that increases as you compress it, the work you do on it gets trapped in there, then that's no longer the case, and you have to allow for the fact that the specific heats of the material have some impact on it. And so this expression is no longer true, and this expression is, where this factor, typically about 1.4 for air anyway, is a multiplier, an exponent, p rho to the power k is a constant. So it depends on how you compress the gas. The resistance to compressing the gas is given also in terms of this stiffness, if you like, the bulk modulus. And so we can define the bulk modulus as the change in volume relative to the change in pressure that you apply. Apply a volume change, the pressure increases, and the ratio of those two gives the magnitude of this compressibility. You can also write it in terms of densities, as this. And what we can do is we can look at how pressure will change, the ideal gas law will change as a function of compression. And, well, I usually derive it, but we're running out of time, so I won't. But a very interesting observation, which you can manipulate just from playing with the ideal gas law, is that the bulk modulus of a gas, at least at very low pressures, is equal to its pressure. And so if we know what the pressure is at atmospheric pressure in this room, we immediately know that the modulus of the gas, the bulk modulus of the gas, is equal to 101 kilopascals. It may seem that that's kind of an abstract phenomenon, but it's important because the speed of sound, how quickly you're hearing me speak, is controlled by the modulus because it's a function of the, actually it turns out that the speed of sound, which we'll talk next time, the P wave is equal to just the modulus divided by the density, all square root. So if you know what the pressure is, you therefore know what the density is. If you know what the pressure is, you know what the modulus is. If you know what the modulus is, you know what the density is also from the ideal gas law. And from both of those, you can calculate immediately what the speed of sound is in air, which we'll talk about next time.